Open delta transformers, in comparison to standard delta transformers, exhibit a reduced power output, specifically delivering approximately 58% of the capacity of a closed delta configuration. This characteristic stems directly from the fundamental design difference. Open delta transformers operate using only two of the three available phases of a three-phase power system. In a conventional closed delta transformer setup, each of the three phases contributes equally to the overall power delivery. These three phases are interconnected in a triangular configuration, often visualized as a Greek letter delta, hence the name. This configuration ensures a balanced distribution of the load across all three phases, leading to efficient utilization of the source power. By contrast, an open delta transformer omits one of these phases, essentially functioning with an incomplete delta connection. This omission results in a less efficient power transfer, as the transformer is not fully leveraging the capacity of the three-phase system. The absence of the third phase creates an imbalance in the current flow and voltage distribution within the transformer. This imbalance leads to increased current flow in the remaining two phases to compensate for the missing phase. However, this compensation is not perfect, and the overall power output is significantly reduced. Furthermore, the increased current can lead to higher losses within the transformer itself, primarily in the form of heat dissipation due to the resistance of the windings. This not only reduces the transformer's efficiency, but can also potentially shorten its lifespan due to thermal stress. The reduced power output is not simply a linear two-thirds of the closed delta capacity. The specific value of 58% arises from the vector relationships between the voltages and currents in a three-phase system. When one phase is removed, the remaining two phases cannot fully replicate the balance conditions of a complete delta configuration. The vector sum of the currents and voltages results in a lower overall power transfer capability. While open delta transformers are less efficient in terms of power delivery, they do offer certain advantages in specific applications. Firstly, they are more economical to install initially, as they require only two transformers instead of three. This reduces both the upfront cost of the transformers themselves and the associated installation labor. Secondly, open delta configurations offer a degree of redundancy. If one of the two transformers fails, the system can continue to operate, albeit at a reduced capacity. This can be critical in applications where even a temporary loss of power is unacceptable. Thirdly, an open delta transformer can be used as an interim solution when a load is expected to increase in the future. Initially, an open delta configuration can be installed to meet the current load requirements. Later, when the load increases, the third transformer can be added to complete the closed delta configuration, thereby increasing the transformer's capacity without requiring a complete replacement. The selection between an open delta and a closed delta transformer configuration depends largely on the specific application and its requirement. If efficiency and maximum power output are paramount, a closed delta configuration is generally the preferred choice. However, if cost savings, redundancy, or future expandability are more important considerations, an open delta configuration may be a more suitable option. When analyzing transformer configurations, several key concepts are crucial to understanding their behavior. Firstly, impedance. Impedance is the total opposition to current flow in an alternating current circuit, encompassing both resistance and reactance. The impedance of a transformer winding affects the voltage drop under load and influences the transformer's ability to deliver power. Secondly, turns ratio. The turns ratio is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. This ratio determines the voltage transformation between the primary and secondary sides of the transformer. Thirdly, vector groups. Vector groups describe the phase relationships between the primary and secondary voltages in a three-phase transformer. Different vector groups have different phase shifts, which can be important for paralleling transformers or connecting them to existing power systems. Fourthly, core material. The core material of a transformer affects its efficiency in magnetizing current. Commonly used core materials include silicon steel and amorphous metal. Silicon steel offers a good balance of cost and performance, while amorphous metal provides higher efficiency but at a higher cost. Fifthly, insulation. Adequate insulation is critical for preventing electrical breakdown within the transformer. The insulation must be able to withstand the voltage stresses imposed by the transformer's operation. Sixthly, cooling methods. Transformers generate heat due to losses in the core and windings. Various cooling methods are employed to dissipate this heat, including air cooling, oil cooling, and forced air or oil cooling. The choice of cooling method depends on the size and power rating of the transformer. Seventhly, tap changers. Tap changes allow the voltage transformation ratio to be adjusted, typically in small steps. This can be useful for compensating for voltage variations in the supply or load. Tap changers can be either on load or off load, depending on whether they can be operated while the transformer is energized. Eighthly, protection devices. Transformers are typically equipped with various protection devices to prevent damage from overloads, short circuits, and other abnormal conditions. These devices may include fuses, circuit breakers, and protective relays. Ninthly, harmonics. Harmonics are voltage or current waveforms that are integer multiples of the fundamental frequency. Harmonics can cause various problems in power systems, including increased losses, equipment overheating, and interference with communication systems. Transformers can either generate or exacerbate harmonics, depending on their design and operating conditions. Tenthly, inrush current. Inrush current is a large transient current that flows when a transformer is initially energized. This current can be several times larger than the normal operating current and can cause nuisance tripping of circuit breakers. Inrush current is caused by the sudden magnetization of the transformer core. When troubleshooting issues with transformer configurations, consider these steps. Firstly, verify voltage levels. Ensure that the input and output voltages are within the specified ranges. Use a voltmeter to measure the voltage at various points in the circuit. Secondly, check for balanced loads. Uneven loading can cause overheating and reduced efficiency. Use an ammeter to measure the current in each phase. Thirdly, inspect for loose connections. Loose connections can cause voltage drops and arcing. Visually inspect all connections and tighten any that are loose. Fourthly, examine the insulation. Damaged insulation can lead to short circuits and ground faults. Use a megameter to test the insulation resistance. Fifthly, check the cooling system. Overheating can damage the transformer. Ensure that the cooling fans are working and that the cooling oil level is adequate. Sixthly, analyze harmonic content. Harmonics can cause various problems. Use a harmonic analyzer to measure the harmonic content of the voltage and current waveforms. Seventhly, monitor temperature. Excessive temperature indicates overloading or cooling problems. Use a thermal imager to monitor the temperature of the transformer components. Eighthly, assess oil quality. In oil-filled transformers, the oil can degrade over time, reducing its insulating properties. Obtain an oil sample and have it tested for dielectric strength and other parameters. Ninthly, review protection settings. Incorrect protection settings can lead to nuisance tripping or failure to protect the transformer in the event of a fault. Verify that the protection settings are appropriate for the application. Tenthly, test the tap changer. If the transformer has a tap changer, test it to ensure that it is operating correctly. Verify that the voltage changes as expected when the tap position is changed. When comparing open delta and closed delta transformer configurations for specific applications, consider these factors. Firstly, load requirements. Assess the total power demand of the load. Closed delta is preferred for high power requirements, while open delta is suitable for low power needs. Secondly, efficiency needs. Determine the importance of energy efficiency. Closed delta offers better efficiency, reducing energy consumption and operating costs. Thirdly, redundancy. Evaluate the need for backup power. Open delta provides redundancy as it can operate with one transformer failed, but at reduced capacity. Fourthly, budget limitations. Consider the initial investment cost. Open delta is more cost-effective initially due to fewer transformers required. Fifthly, future expansion project potential load growth. Open Delta allows for easy upgrade to closed Delta by adding a third transformer. Sixthly, voltage regulation assessed sensitivity to voltage fluctuations. Closed Delta generally provides better voltage regulation under varying load conditions. Seventhly, harmonic distortion. Evaluate the potential for harmonic generation or amplification. Closed Delta is less susceptible to harmonic issues compared to open Delta. Eighthly, space constraints. Consider the physical space available for the transformer installation. Open Delta requires less space compared to closed Delta due to fewer components. Ninthly, maintenance accessibility. Evaluate the ease of maintenance and repair. Open Delta might offer easier access to components due to simpler configuration. Tenthly, specific industry standards. Adhere to relevant electrical codes and standards for transformer installations in your region. To further elaborate on transformer design considerations, there are firstly, core design, which the core is the magnetic circuit of the transformer and is typically made of laminated silicon steel or amorphous metal. The core design affects the transformer's efficiency, magnetizing current, and ability to withstand short-circuit forces. Secondly, winding design. The windings are the electrical conductors that carry the current and create the magnetic flux. The winding design affects the transformer's voltage ratio, impedance, and ability to handle overloads and short circuits. Thirdly, insulation design. Adequate insulation is crucial for preventing electrical breakdown within the transformer. The insulation must be able to withstand the voltage stresses imposed by the transformer's operation. Fourthly, cooling system design. Transformers generate heat due to losses in the core and windings. The cooling system design must be adequate to dissipate this heat and prevent the transformer from overheating. Fifthly, tank design. The tank houses the core and windings and provides mechanical protection. The tank design must be strong enough to withstand internal pressure and external forces. Sixthly, bushing design. Bushings provide a means of connecting the transformer windings to the external power system. The bushing design must be adequate to withstand the voltage and current stresses imposed by the transformer's operation. Seventhly, tap changer design. Tap changers allow the voltage transformation ratio to be adjusted. The tap changer design must be reliable and easy to operate. Eighthly, protection system design. Transformers are typically equipped with various protection devices to prevent damage from overloads, short circuits, and other abnormal conditions. The protection system design must be coordinated with the transformer's characteristics and the power system to which it is connected. Ninthly, noise reduction design. Transformers can generate noise due to vibration of the core and windings. Noise reduction design techniques can be used to minimize the noise level. Tenthly, seismic design. In earthquake-prone areas, transformers must be designed to withstand seismic forces. Seismic design considerations include the use of stronger tanks, bracing, and anchoring systems. In the context of electrical codes and standards related to transformers, there are several key aspects. Firstly, National Electrical Code, NEC Article 450 covers the installation and wiring of transformers. It specifies requirements for overcurrent protection, grounding, ventilation, and location. Secondly, Institute of Electrical and Electronics Engineers, IEE standards. IEE offers various standards related to transformers, including standards for testing, performance, and safety. IEE Standard 57.12.0 covers the general requirements for liquid-filled transformers, while IEE Standard 57.12.90 covers the test code for liquid-filled transformers. Thirdly, National Electrical Manufacturers Association, NEMA standards. NEMA provides standards for the construction and performance of transformers. NEMA Standard 720 covers the dry-type transformers for general applications. Fourthly, Underwriters Laboratories, UL listing. UL listing indicates that a transformer has been tested and meets UL safety standards. UL Standard 506 covers the specialty transformers, while UL Standard 1561 covers the dry-type general purpose and power transformers. Fifthly, International Electrotechnical Commission, IEC standards. IEC offers international standards for transformers, which are widely used in Europe and other parts of the world. IEC standard 60076 covers the power transformers. Sixthly, energy efficiency standards. Various countries and regions have implemented energy efficiency standards for transformers. In the United States, the Department of Energy (DOE) has established minimum energy efficiency requirements for distribution transformers. Seventhly, environmental regulations. Environmental regulations may apply to transformers, particularly liquid-filled transformers containing oil. These regulations may address issues such as oil spill prevention and disposal of contaminated oil. Eighthly, local codes and regulations. Local electrical codes and regulations may impose additional requirements for transformer installations. It is important to consult with local authorities to ensure compliance with all applicable codes and regulations. Ninthly, grounding requirements. Proper grounding is essential for the safety of transformer installations. The NEC specifies detailed requirements for grounding transformer windings and enclosures. Tenthly, overcurrent protection. Transformers must be protected against overcurrents to prevent damage from overloads and short circuits. The NEC specifies requirements for overcurrent protection devices such as fuses and circuit breakers. Discussing the practical applications and limitations of open delta transformers further. Firstly, temporary power supply. Open delta configurations are often used as a temporary power supply solution when a full three-phase system is not yet available or when the load is relatively small. Secondly, rural electrification. In rural areas where the cost of installing a full three-phase distribution system is prohibitive, open delta transformers can provide a cost-effective solution for supplying three-phase power to farms and other rural customers. Thirdly, small commercial buildings. Open delta transformers can be used to supply power to small commercial buildings such as retail stores and restaurants. However, the load must be carefully balanced to avoid overloading one of the transformers. Fourthly, motor starting. Open delta transformers can be used for starting large motors. However, the voltage drop during starting can be significant, which may require the use of reduced voltage starting methods. Fifthly, emergency power. Open delta transformers can provide emergency power in the event of a power outage. However, the capacity of the open delta transformer may be limited, so it is important to carefully assess the load requirements. Sixthly, limitations. Power imbalance. Open delta transformers are more susceptible to power imbalance than closed delta transformers. This can lead to voltage regulation problems and increased losses. Seventhly, reduced capacity. The capacity of an open delta transformer is only 57.7% of the capacity of a closed delta transformer with the same size transformers. This means that the transformers must be larger to supply the same load. Eighthly, increased voltage drop. Open delta transformers typically have a higher voltage drop than closed delta transformers. This can be a problem for sensitive loads that require a stable voltage. Ninthly, harmonic distortion. Open delta transformers can be more susceptible to harmonic distortion than closed delta transformers. This can be a problem for electronic equipment that is sensitive to harmonics. Tenthly, phase shift. The phase shift between the primary and secondary voltages in an open delta transformer is different from that in a closed delta transformer. This must be taken into account when paralleling transformers or connecting them to other power sources.